All right. So welcome to week 1 of the Aggregates lab. Actually, look, give me one sec. I'm going to make sure. Yep. All right. I've got it optimized for video sharing. So this is the aggregates portion of your lab, and we will go through and do 2 weeks worth. Let me see. There we go. We'll do 2 weeks worth of labs for aggregates. This first one will cover those highlighted: unit weight or bulk density. It's the same thing. It's referenced bulk density in some parts of the assignment and unit weight and some others. It's just how it is. But they're both the same thing. Sieve analysis is run. We'll see a video on that. There's coarse and fine aggregate specific gravity. You'll understand that a little bit more. And LA abrasion. They're all just kind of names for procedures that we do to test aggregates. And next week we'll check 4 more tests, but I won't get into those. So week 1, so bulk density and voids. So unit weight. First off, I'll give that the ASTM is C128. That's in your lab file folder for the aggregate specifications. It's called the standard test method for bulk density and voids in aggregate. And then these values are good to determine mixed proportions for concrete. And bulk density can be used in mass volume relationship calculations. So if you know that your like your concrete slab is going to be 6 inches deep and 12 feet by 12 feet, then you would need to figure out, hey, like how much aggregate do I need to fill in this? Obviously, you have to make proportions with cement, aggregate, and water. But you would want to figure out, hey, how much can that aggregate actually compact? So what you do is you want to figure out the bulk density of it by compacting it down with this standard method. And it helps you to figure out how much aggregate fits in a specific volume of a measure. That way you can calculate like really how much you would need in a 6 inch deep by 12 foot by 12 foot slab. It helps out with those. If you wanted to fill a hole, how much would you need dirt wise? You do the same thing, but aggregate's different because it's coarse. So the equipment, I didn't provide a picture for this, but it's in the video coming up. So you have a balance or a just regular scale. You have a tamping rod, just a metal rod that's 1/2 inch in diameter. It doesn't really matter, just something good. You could use a piece of rebar if you're out in the field. You have a measure, which is the bowl or container that has a specific volume to it. And you'll see what that looks like. It's just a cylinder, open cylinder on the top, and you just fill in your aggregate there. And then you also have a scoop to scoop your aggregate into. So what you want to do, some of y'all have taken geotech. No, all of you have taken geotech because that's the prereq. There's a test that you do, I believe it's the Proctor, where you rod it with a weight that you drop over and over a few times each lift. And at the end of it, you want to make sure that after your last lift that you're compacting, that your material is just a little bit over the top. So that way you can clear off the top. And that's the same way we want here. We don't want the material to cave in and be a big indentation where we could have had material fill that void, because then our calculation is off for our unit weight or that bulk density and how much we need for in mass to fit that volume. So for this test, we need like 6 kilograms of material, which is like 12, 13 pounds. So I've got a video coming up. The procedure that I'll run through in this video, you fill it 1/3 full, you tamp it with 25 strokes with the rod, then you fill it 2/3 full, you level it, tamp it with the rod 25 times, then you feel the measure overflowing, like 125% of the volume. You want to tamp it with 25 strokes, and then you level it off with the straight edge. I just use the tamping rod, and I talk about that. And then you measure the mass of the measure container, the bowl, and the aggregate inside of it. Once you're done recording that value, then you dump back out all of the aggregate, and you weigh the measure alone, and then you're able to calculate that bulk density, how much mass can fit in that specified volume. It helps you for anything if you do need to do a slab, if you need to make a 1 foot by 1 foot by 1 foot cube for some reason, like you could determine that based on this bulk density. So here's the video real quick. Hopefully y'all can hear it. If you can't hear it, let me know. But I've optimized it, I think, to where you should be able to. Oh gosh, that's not what I wanted. Hang on, my mouse disappeared. There we go.
We're going to be doing the unit weight or bulk density of aggregate. So this is our measure that we use to do the test. We have a tamping rod, we have our aggregate, and a scoop to fill it up. And then we also have a scale over there. So what we're going to be doing, we want to test all of our aggregates with this. The only test that we're going to do today for the recording is limestone, but you can do it with limestone, granite, gravel, and sand. So the procedure is you want to fill it up in 3 separate lifts, a third of the way each time, and then you tamp it 25 times each lift, and after that you clear off the top and you go weigh it on the scale, record that weight, and then you record the empty weight of it. So I'm going to go ahead and start the procedure. So I'll fill it up 1/3 of the way. There's 1/3, and then I will and then another 1/3. And then 25 more rods. And then for the last lift, we want to fill it over the top so that when we're done tamping it, it has not gone below the rim, because we want to be able to clear off the top. And you'll lose some aggregate over the side, but that's okay. So 25 more rods. So that was good. Now what we'll do is you want to clear off the top. And so you roll it backwards to push the aggregate away, because if you roll it forwards, you're going to push aggregate down. We don't want that, because that's not of the 25 tamps. So if there's any aggregate that won't budge, you can pull it out and continue going. This is what the specification says. If it does not fit and you cannot clear off the top, then you can pull it out. There we go. And then we weigh this over here. $6,352.4. And then we weigh the empty measure. 1,826.4. And then you use the calculations to determine the bulk density of your limestone, and then you do that for all the other aggregate types.
So I hope that makes sense for y'all. Let me check and see if any of y'all have any questions so far, chat. Sorry, yeah, thanks for joining. And Landon, hopefully, Landon, did you get to watch this video? You can just send me a message. So I've only gone through the bulk density. Pretty much for bulk density, you want to figure out how much material can fit in a specified volume so that you can get mass to volume relationships for making a concrete slab or making an asphalt road. So I won't talk about that anymore. If you have comments or chat, if you want to say that the video looks kind of bad, let me know in chat too. That way I can hopefully get it fixed. But we'll go ahead and move on to the next portion of lab. Let's see. So the next portion is sieve analysis. The ASTM is C126. It's called the standard test method for sieve analysis of fine and coarse aggregates. So what you do is you determine an aggregate gradation based on the particle size distribution of the aggregates. You make sure it's in compliance with project specifications. So each specification or each different job might have a different gradation required. And I'll go into what a gradation is after the video. But the gradation is used to determine porosity and packing of the material. Just like you saw in the unit weight or bulk density, if you use only limestone, you're obviously going to have a lot of pore spaces because the aggregate's so big. So you might need a gradation of some coarse, some fine, maybe some dusty, so that it fills in all those voids. And then also gradation on different materials or stockpiles are used. That's pretty much exactly what I said. So for concrete, people would use limestone, sand, cement, and water. Cement's the glue that binds it together, and then sand fills in the pores of the larger aggregate. So the equipment that you need for this test, obviously you need a balance or a scale again. You need sieves, and there's a picture of 7 sieves right there, different sizes. Those are actually for different tests because you'd use the same diameter sieve for the same test at once. So I don't know why they would provide a picture of a bunch of sieves that are 12 inches in diameter all the way down to 4, maybe because 4 is used in another test and they want to show that they come in different sizes too. But they have different openings. That one in the middle is probably an inch opening. That would probably let limestone through, or that specific limestone that we looked at. And then the other sieves have different size openings, and I'll show you that a little bit more. You have a mechanical sieve shaker because we don't want to sit there and shake it on our own. That'd be really hard. And then you have an oven because you have to dry out the material prior to actually testing. So the sampling technique, you need to get a sample for fine aggregates of 300 grams. If it's coarse, you want a sample size of between 1,000 and 1,500 is pretty good. It's determined by the nominal maximum aggregate size, but for coarse aggregate, for mixtures, mixtures that are both fine and coarse, so that are real big in size and real dusty, you want to use that coarse recommendation because you have coarse in it. You don't want to use a small sample of 300 grams because one of those limestone rocks could be 20, 30, 40 grams right there, and that's not going to really help you figure out what distribution your sample is. So you want a bigger sample, 1,000 to 1,500. So prior to doing the test, you wash your aggregate, make sure you remove any clay, any dirt, maybe vegetation if it was sitting in a stockpile. You clean that off, and then you want to dry the sample. You don't want the aggregate wet when it's going through those sieves. Some of them that are smaller are a little bit more fine, and so if it gets wet, it's not going to pass through. So you want to dry it in an oven that's about 200 degrees, 250 degrees Fahrenheit, 105 to 115 C, until there's no mass change. That means that all of the water has evaporated. Next, you choose the appropriate sieves that you need for testing. Stack them in descending order from biggest on the top all the way to smallest on the bottom. That way, smaller aggregate passes through all the others until it stops at the one it needs to. And then if needed to, you can split the sample into multiple quantities and sieve the material. That's if you have so much of one size aggregate where it's not going to let any other rocks pass through it, or if your sample is huge. Like I've done a sample that's 3,000 grams, and I've needed to break that into two, and it takes a lot more time because you got to do the procedure twice, but that's just what you have to do in some instances when you can't get a smaller sample. Then what you do is you dump all of your aggregate into the top of the sieves. You use a mechanical shaker for 5 minutes. Then you remove the sieves from the mechanical shaker. You weigh each sieve or the material retained on it, and you report the mass on each sieve cumulatively. So I guess I'll explain this a little bit afterwards. So I won't get into it now. And then what you do is you calculate percent retained, percent passing, and the fineness modulus of the material that you've passed through it. So we'll go ahead and watch another video. If you have a comment on it, go ahead and send it in chat. I would appreciate it if you do that. That'd be awesome. So we'll get started.
Now we're going to be doing sieve analysis. We need a stack of sieves for that, and we have all of these right here, ranging from 3/4 inch all the way down to the number 200 sieve right here, and then a pan to catch anything that's smaller than that. These sieves, you stack them in large, so the large opening size all the way down to the very small dusty size. So I'll show you what this looks like. So this is the 3/4 inch sieve. Here's a smaller one. This one is a number 8 sieve. And then the number 200 is right here. And this catches dust in it. It's 75 microns, very, very fine material. So what we want to do is we want to pour our aggregate in there and sieve it out to figure out our gradation. Before we do that, we need to weigh our material. So we'll come over here to zero the bowl and then dump all of our aggregate and all the dust. And for this one, we're using river gravel. So right now we have 1,305.7 grams of aggregate. And then what we'll do, we got our sieves together. Dump it in the top, and then put your lid on tight securely so no dust escapes, and then we'll take it to the machine. So this is the machine right here. These paddles hit each of the different sieves and so that it can shake the material through them and work it down to where the material size actually is. So we'll just go ahead and set this in here like that, and it will rotate as well. So we'll go ahead and start it.
So that machine is pretty loud. You let it run for 5 minutes, and then you do the last half of the procedure. So I got that right here.
Then we'll take it over here so we can weigh it. So for doing sieve analysis, you want to get a cumulative weight. I'll get this for you, thank you. So we're getting a cumulative weight. So we'll eventually at the pan, we'll have the total weight that we had, or we should, which was 1,305 grams. So what we'll do is we have all this material, zero to our scale. You want to get all of the aggregate. So 251. That was on the 3/4, 251 grams. That one was 0. All right, next, 1/2 inch. You can push them through with your finger sometimes. Sometimes you gotta work it a little harder. Use a screwdriver. There we go. All right, record it. Can't forget that. 659.8. All right, the next one is the 3/8. There we go. 899, sorry. 0.1 grams. Next one. See if I can go a little quicker. All right, got that. 1211.7. And once things get smaller, you can't really get everything, so you just try and do your best. And one little tiny rock's not going to change the weight a whole lot, so it's not a huge deal to get every single one. Smaller and smaller. So right there, we only added about 25 grams for the number 16. Here's the number 30. It's getting less and less. This is because it's river gravel. 1294.7. Finer and finer dust. 1308. $1302.6. Here's our 200 sieve. So it looks like not a whole lot. Changed it by 0.2 grams. Still need to record that. And then our pan. So that's everything smaller than a 200. There we go. 1306.0 grams. So we added 0.3 grams because we cleaned it up a little bit more than the last person that did this test.
All right, so that was that video. I have another video that I did not put in the PowerPoint, and it's actually me doing the last gradation part for sand, and I forgot to add it in, but I'll upload that to Canvas, since that is, I'm going to upload all the separate videos on their own without this PowerPoint. That way y'all can go through and see how a procedure works if you needed to be remembered on it. And so I showed you kind of what sand would look like. You all know how to run a sieve analysis test from watching that video, I hope, but you can go see kind of how that looks differently. And this, I wanted y'all to see what a gradation will look like. This is what an aggregate gradation chart looks like for percent passing. And this is actually how you would want to label and like make your graph look. I upped the font. I changed all of the font to be black. And then right here, I've got log scale. And you can do that easily by clicking on these numbers down here and going and changing that. But I wanted to show you just that's kind of how it looks. So aggregate 2, aggregate 1's right here. You can see that for 1, 2, 3, 4, 5, 6, 7, those are all less than, let's see. Oh, you know what? I'm glad I'm recording this. This is actually a mistake. I have this is in inches, so I would get -1 point here. So these like 5, 6 sieves right here didn't really have anything past them. Those are the smaller ones. So this means that this material, all of this is the coarser stuff. So this is probably the limestone. And then this right here, it starts to dip, and there's a huge, I mean, all of your sand, this is actually sand, so all of it passes between 1, 2, 3, 4, 5, 6 sieves instead of all 10. So you can blend the aggregate in different proportions and get different different gradations that you want. You could mess with percentages of them all. So obviously sand is more fine because it's towards the smaller sieve opening size, and this aggregate 1 is limestone, and it's a lot coarser because it's towards the larger that it starts to drop. So you can see these, how they look different. There's 2 different limestones. Limestone 53 is a blend of a bunch of different sizes, some big, some small. Limestone 8 is kind of the same size, and so on. So these would all look completely different on this gradation chart. So that's what I have for sieve analysis. We'll get into the last 3 real quick. Next is coarse aggregate specific gravity and absorption. The ASTM standard is C127, and it's called the standard test method for specific gravity and absorption of coarse aggregate. Bulk specific gravity, it's a vital property for volumetric calculations. And then apparent specific gravity, y'all will hear bulk specific gravity, apparent specific gravity a lot. I hope that you're able to remember which one is which, especially with like your symbols in like reports and symbols for keeping track in equations. It is kind of hard to get used to at first, but it shouldn't be too bad once you kind of do it a few times. But apparent specific gravity relates to the density of the solid. It excludes the pore space of the aggregate. So every aggregate has little holes kind of in it that are microscopic. The apparent specific gravity does not include that. So the equipment for this test, you have a balance or scale right above. You have sieves because you want to make sure that you're testing on the same size aggregate, so you don't actually use it in this test. You use it to prep this test. Then you also have a water tank and a basket that you can dunk underwater, and a towel to dry off the aggregate. The sampling technique, you get a minimum weight for the test sample. It can be anywhere from 1,000 to 1,300 grams roughly, but you get aggregates passing the number 4 sieve, which is probably, I believe it's 4.75 millimeters is what it is. Number 4 doesn't mean 4 millimeters. They start dropping after the 3/8 inch sieve, and they go like number 4, number 8, number 16, number 30. Those don't relate to the actual opening as like in millimeters. It's a different standard. Then what you do, so approximately 2,500 grams of dry aggregate will be used, and so you're using the coarser stuff. Dry the sample again, make sure there's no mass change, no water in the aggregate. What you do is you let it cool. Then what you want, actually you wanted to wash the aggregate before, sorry. And what you do is you submerge the aggregate in water at room temperature for 24 hours. Actually, that is correct. So you dry the sample, then you want to wash it off completely, submerge it for 24 hours. That way, all of that pore space is filled in the aggregate. So right there, you can see on the bottom right, that's what your aggregate roughly would look like, not like a snowflake, but you get the idea that there's those pores along the aggregate's face, and they can be permeated by water. And so what you want is you want to let that aggregate soak for 24 hours so that water can soak into it, because if you put it in water for an hour, it might not soak into some of those smaller pores. So after you have soaked it for 24 hours, which is when we would start the lab, we would remove the sample from water. You'd roll it in an absorbing cloth to remove the excess surface water. So that way you only have what's on that picture where the pores are filled. And then you weigh the samples, and that's the saturated surface dry. So your aggregate is saturated, but the surface is dry. So if you dunked a rock underwater and pulled it back out, it'd probably be shiny because the water's coating it. But what you want to do is you want to pat it with a towel lightly to remove that shiny surface, that shiny water on the outside of it. That way you can figure out, hey, how much pore space is there? Is there water in those pores? And you can record that value, and that is your saturated surface dry. That is a really important thing. We do it for asphalt samples. We do it for aggregates on their own, for wrap, just for different things to figure out volumetric conditions that we need. So then after you've gotten that SSD, So you've already dried off the aggregate with a towel on the outside lightly. You record that weight. After that's done, you want to submerge it in a tank for 3 minutes in that basket hanging under the scale or the balance. And after 3 minutes, you record the weight. That's going to be your submerged weight. And then what you do is you dry this, you take the sample out and then you dry it in an oven for 24 hours overnight. That way you can get rid of any moisture in the aggregate at all. And then you cool it down and weigh it again. So you have 3 weights right after that. You have your saturated surface dry, which is where there's water inside the aggregate, but it's like the aggregate is obviously exposed to air. The second one is the submerged weight, where I believe it's the aggregate weighs like 60% of what it would out of air or out of water, sorry. And then you have the completely dry aggregate, and you're able to figure out different calculations. We'll listen to this. This is done by Jason Moore at NCAT. He's great at what he does. He's the lab manager at NCAT, and a really informational video here. It's not too long, but just bear with it. Oops, waited too long. Here we go.
So for specific gravity of our coarse aggregates, we follow ASTO T8.
Oops, sorry guys.
5. And for ASTO T85, we'll need our coarse aggregate basket. We'll need a bulk station because we have to weigh our sample underwater, because for this specification, there will be 3 things we're looking for. We have to get the dry weight of our sample, we have to get our SSD weight of our sample, and SSD stands for saturated surface dry, and then we also have to get our underwater weight. So our sample size for this specification depends on the nominal max of our aggregate. If you look up in T85, there's a chart table in that specification that gives you the nominal max and the weight needed for the nominal max. So we've already got our samples together. Again, this is ran on coarse material, so number 4 and above. Once you get your sample size, you want to wash the dust off, and then you want to soak your sample for 15 to 19 hours. After 15 to 19 hours, we can begin the test. So our sample's been soaked in 15 to 19 hours. I'm going to go ahead and pour some of this excess water off of it. Now, the first weight I'm going to get for this sample is my SSD weight, which is our saturated surface dry. So to do that, we have to have a damp towel. And in the specification, it says you need a damp towel, and they refer to damp as when water cannot be wrung out of the towel. So for this towel, I've already dampened it, but I'm going to check it to make sure we can get most of the water out of the towel. The reason we do this, or the reason we need a damp towel, is because we are determining our SSD weight. Like I said, SSD stands for saturated surface dry. Where our sample is saturated because it's been soaked in water, so I want to determine what our saturated sample is with the surface dry. I don't want to pull the water out of the voids in these aggregate particles, so we do that with a damp towel, because a damp towel will just draw off the surface and will not pull the water out. If you use a dry towel could possibly pull the water out of the voids of our aggregate particles. So you just place your sample in your damp towel. And you just pat it dry. And this only takes a couple of minutes. And the way that we determine if our sample is an SSD is when our aggregate particles are not shiny or glossy anymore. You see this particle here, it might be hard to see in the camera, but it is still shiny. So that means it still has a lot of water on the outside of it. So I just take my damp towel, go back and forth across the sample, just trying to get that surface water off my sample until I determine that my sample is not shiny or not glossy and is at SSD. For large particles that tend to still look shiny, it's okay to pick them up individually and kind of block them off if you would like, if they do not seem to be getting dry. So I'm going to take my bowl that I soaked my sample in, and we'll just pour our sample in our bowl to get our SSD weight. So I believe we've got most of our water, or most of our surface water off our sample. Our particles are not shiny and glossy looking now, so I believe they're in their SSD condition. So this will be the first weight that we take. Some of the sample has fell out onto the floor. That's okay if you lose a particle or two because you haven't taken a weight yet. With this weight, we want to make sure we don't lose any more of the sample when we're transferring it to the basket and also getting the dry weight. So I'm recording my SSD weight of my sample. And now we have our coarse aggregate baskets. This is how we get our underwater weight of our sample. We can just hang it right in our bulk station. And you want to be sure that you zero out this basket because this is what we're using to get our underwater weight. So I zeroed out my basket. I'm adding the sample to the basket, being sure not to lose any of the material. Also, for this test, your water bath should be 23 degrees Celsius plus or minus 1.7 degrees. I know a lot of the testing that we do, typically a water bath is 25 degrees Celsius, but for AASHTO T85, it actually states 23 degrees Celsius. So I'm just adding my basket to my water bath. A couple of things you want to check while your basket's in your water bath is make sure that your basket is not touching the bottom of the water bath or the sides. I like to put my hand in and just gently move it back and forth to make sure nothing's touching it. If this basket is touching the bottom or the sides of your water bath, it's going to throw your scale off and your weights are going to be incorrect. A lot of times too, I'll take my basket and just shake it a little bit. Just do it gently, and that helps release some of the air bubbles that may be inside the sample. Now, to get your underwater weight, you just want to wait till your scale balances out. There's no set time in the specification. Usually this takes a minute or two until our scale balances out, and then we'll record this weight for our underwater weight. So the scale's balanced out, so I can record my underwater weight. Then now we can remove our sample from the basket. And when I was discussing, make sure your handle is under the water. Your basket is hanging like so. You want to make sure this handle here is completely underwater. Your water level should be at least an inch above that handle. If your water level only comes up to about halfway on your handle, it will give you an incorrect weight. So now we have our SSD weight, we have our underwater weight. We can add our sample back to the bowl. And now I will place it in the oven. And that oven should be set at 110 degrees Celsius until our sample dries back to get our dry weight. What we tend to like to do, if you can put your sample in an oven overnight, it will be dry when you come into work the next day.
So that's the procedure for it. I hope that makes sense for y'all. The next one we're going to look at is fine aggregate specific gravity and absorption. So you're trying to find the same things. You're trying to find that SSD where your You don't have the outside of the aggregate still coated in water, you just want the inside, but obviously you're doing it for fine aggregate. So think about sand. If you had sand and you wanted to figure out a submerged weight, you probably wouldn't want to dump a scoop of sand into that bucket or that basket that they had, because then it would just fall through right to the bottom of that barrel. So there's different ways to do it. And Jason also has a video for this one. We'll see that in just a little bit. But the ASTM for this one is C128, standard test method for specific gravity and absorption of fine aggregate. Again, same thing, bulk specific gravity, apparent specific gravity, it's the same thing for both of them. So the materials you need are a little bit different. Instead of a bucket with water and a basket, you have, obviously you have a scale, you need that. There's a pycnometer, which is that glass bulb looking, I guess, sciencey looking thing. And they use that to determine the submerged weight, and you'll see how he does that. There's also a cone-shaped mold. It's the gold thing in the middle. There's a metal tamper. You have to have a pan so you don't lose your sample everywhere because it gets kind of messy. And a hair dryer, and that helps you dry out your sand. So the sampling technique, you take about 1 kilogram of fine aggregate or sand to run in this test. And the test needs to be passing the number 4 sieve. On the prior one, you wanted it to be larger than the number 4 or retained on the number 4. But this, we want it smaller. So the procedure for this one, dry the sample until it's completely dry. Then what you want to do is you want to cover the aggregate with water. You can let it soak for 24 hours again. This would be done before y'all had even showed up to a lab. But that way there's moisture in the sand that has been soaked into all the pores of it. Then what you do is you remove the excess water from the sample by drying it with a hair dryer. It's a very fun activity. It's one of the most entertaining things of the whole lab. Not really. It's pretty boring sitting there for about 10 minutes with a hair dryer just drying sand. I guess you paid to do that. It's kind of funny. But then what you do is you just dry it over time, stir in the material, let it all kind of dry equally throughout. That's why you want to stir it. And then you conduct the cone test. And you try and see if there's moisture in it. So y'all have all made a sandcastle, I hope. If you make a sandcastle, if it's wet sand, it's going to stick and it's going to stay the same shape as whatever you put it in. If you have dry sand, it's not going to stay up at all. So what we want is we want there to be some moisture in there. And the way that that's done is by filling up this cone with sand that's moist. And if you remove the cone and the entire cone stays still, like a wet sandcastle, then your sand is too wet still. You need to get still dried out some. But if your sand collapses completely, you know it's too dry, so you have to add moisture to it. So you use that little tamping rod 25 times, and you just tamp it very lightly, remove the cone. If one side slumps instead of the entire thing, then you know that it is an SSD condition. So here's just a little picture I got for you. On the left, it looks like that could be like some small, I don't even know what aggregate actually, but that's a fine aggregate, and it has too much moisture in it. You can see it didn't collapse at all. And then on the right, that's some sand, and there's too little moisture. It collapsed completely. You just want half. So we're gonna start this video real quick. This one's one of the longer videos. But this test is kind of finicky. It's not fun to do in the lab in person because it kind of goes over your head. So hopefully Jason's able to help you understand it a little bit more. And again, if you have comments, if you think the video is not doing it too great at explaining it, you can leave a message in the chat box and I will attend to that immediately. Here we go.
AASHTO T84. This is the specification we use for determining our aggregate specific gravity of our fine aggregates. And we'll also use this test to determine the absorption of our fine aggregates also. The equipment needed for this test is, well, we have to have our fine aggregate sample. we have to have the cone and tamp because we'll be determining the SSD weight of our aggregate. And then we'll also have to have a picnometer here that will put our SSD sample in and remove the air to determine what our weight underwater may be for our fine aggregate sample. And then finally, we'd get the dry weight. So those are the 3 weights needed to determine the specific gravities of our fine aggregates. So AASHTO T84, we have to have our sample, we have to soak it in water for 15 to 19 hours. That is just the same as we do for coarse aggregates. But for a fine aggregate sample, we don't actually have to cover the sample underwater. We just have to make sure we have at least 6% moisture in our sample while it soaks. The easiest way to do that we have found is to take a Ziploc bag, put your aggregate sample in, add your 6% water, take your hands and you can just move it around and your fine aggregate sample will soak up that water, let it sit overnight for 15 to 19 hours. And then after that 15 to 19 hours is up, then that's when we can actually begin the test. So we have soaked this sample here. I have it spread out on a pan. And now we want to dry this sample back till it gets to its SSD state. There are several different ways that you can dry your fine aggregates back. Depends on how much time you have. If you have all day, maybe you can let it air dry. I've seen labs take and place fans, just blowing a little air over the top of them to help them dry. Or as you see here, I've seen many people use hair dryers. What you want to keep in mind is if you do use a hair dryer, or even if it's just drying with a fan, you want to come by periodically, stir your sample with a spatula or with your hand to make sure that it's drying evenly. So you don't want to blow all your sample out of your pan. You want to keep your sample in the pan as much as possible. When using a hair dryer, it's always good to stand back a little bit from your sample, let the hot air flow evenly over your sample. What I tend to do is dry it for a few minutes, and then we'll mix our sample back together to make sure everything is drying evenly. Now, I know this sample is not close to SSD yet. It still has a good bit of moisture in there. One way to test to see if your sample is getting close to SSD, a lot of times if you take the palm of your hand and stick it to your sample, if it's really wet still, it'll all stick to your hand. So I would keep drying this a little bit more till I just have a few particles sticking to my hand. So now we've dried the sample for a while, so let's check to see if we're at our SSD state. The way we do that is we have our cone and tamp. I'll clear out an area on the pan, place our cone, and then we'll fill it up with our aggregates. And you can just take your hands and just fill your cone up till it is overflowing. Once it's overflowing, I like to take my hand and kind of brush away the material that's on the outside, because once I remove this cone, I want to see how our fine aggregates slump. So that's what we're looking for. So this is the tamp. We have to do 25 tamps on this material, and it's very small increments that you move it. The specification says it's a 5 millimeter drop. So, and we'll go around the outside as we do this. So that's 25. And now I will remove my cone. And as we see here, our material is not slumping any. So this means we still have too much moisture in our material, and it's not reached that SSD condition. What we would like to see is when I remove the cone off, we would like to see our fine aggregate material slump about halfway. And then that is what we would determine as our SSD condition. But for this sample, we actually need to dry it a little more. So after a few more minutes of drying, we'll now check our SSD condition again. Fill our cone up with our aggregate sample. Take your tamp, 25 drops at 5 millimeters. And that's what we would like to see with a slump. We have just about half our cone slumped, so we would consider this material here at SSD condition. Now, since we're at SSD condition, the next step is to take your picnometer. If you want to get our SSD weight, I'll go ahead and zero out this picnometer. It's also good to put a little bit of water on the bottom. The reason being, if you have a fine aggregate that has a lot of clay-like material in there, if you just dump the material in with no water, it tends to stick to the glass and it's hard to get out. So add the water to the picnometer and then our zero out. And we have to add 500 grams plus or minus half a gram of our SSD material. It's also good if you have a funnel that will help you get your sample into your picnometer. So once we have 500 plus or minus half a gram of material in our picnometer, that is our SSD weight. So I'll record it on our sheet as our saturated surface dry aggregate. So in this example, I'm at 500.3 grams. Now we'll add our distilled water. We want to add enough to cover our fine aggregate sample in our picnometer. You need to add enough water so your sample is completely covered, typically by an inch or two. And now, what we want to do is get the air bubbles out of our sample. We want to make sure that we have enough water in here that our sample doesn't break the surface of this water. And it's always good if you'll tilt your picnometer and shake it with your other hand. And we can see the bubbles as they come out, that is air releasing from our sample. Because what we're trying to do is we want to get all the air out of our sample and then record the weight. So after we have shaken our sample, and typically this takes 10 to 15 minutes, and make sure all our air bubbles are out of our sample, we now need to take our picnometer and fill it up to the calibration mark. Because these picnometers are calibrated with water to their calibration marks. And so we have a value for that, and then we can get a weight of our sample and water filled to the calibration mark and subtract those two, and that will give us our weight of what's considered our underwater aggregate or our picnometer filled with water, as it states on our worksheet here. So we'll fill our picnometer to the calibration mark. Now with some material, like you see here, there's foam and bubbles that tend to rise. We want to get these out of the sample. So for this picnometer here, my calibration mark is where my finger is. So I'm going to add enough water to actually make that foam rise. There's a couple of different ways to get the foam. I've seen labs add what's called liquid aerosol or dropper tube to help get rid of those bubbles. But an easier way too that'll work, just get a paper towel and just stick it down your picnometer. And you can roll it around and help get some of these bubbles out. So once we have gotten all the foam and bubbles out, I will continue to fill to the calibration mark with water. And we want to make sure the meniscus of our water level is at that calibration mark. And what your meniscus is, if you look at your water level, you can see a bubble, and the bottom of this bubble is what we consider the meniscus. Let's add in a little more water. And get it to our calibration mark. And now we need to take this weight. Make sure my scale is 0 out. Now this will give me my weight of my pycnometer filled with water and sample. And so I have recorded that weight, and there's only one other weight we need to get, and that's our dry weight. So the way I would get my dry weight is that I would take my sample and I would just pour it in a bowl. And you want a bowl wide enough like this one because you don't want to lose any of your sample. Because we typically have to add water back to it. It all doesn't come out. So once we have our sample rinsed out of our pycnometer and into the bowl here, we'll now take our sample. We'll place it in an oven at 110 degrees Celsius, which is 230 degrees Fahrenheit, to dry this material back. It's good to take these and dry them back overnight. And then in the morning when you come in, we can take our sample out, let it cool, get the weight of our sample, and then we'll have the dry weight of our fine aggregate sample. And we'll have all the weights we need to calculate the specific gravities of our fine aggregates and the absorption of our fine aggregates.
So that was pretty darn good. Hope y'all followed that. So I didn't really go through this procedure. I waited till afterwards to do it. So I just wanted to go through it real quick with y'all. The pycnometer is that glass bulb thing. You fill it with water, tear it, you get a weight of what the pycnometer is with water in it. Just like you would do with the basket, where you want to weigh the basket underwater for coarse aggregate. You add 500 grams of the sand. That's why you don't weigh the sand until after it's already in the pycnometer, because you're getting 500 grams of that SSD. So your SSD weight is 500. Then you want to fill the specimen with water and then shake out all of the air out of it, and air is trapped all in that aggregate because it's very fine. You shake it for a few minutes and get all that out, remove the foam, fill the sample to the calibration line like Jason did, and then you record that weight, and that is your submerged weight. Once you get that and subtract the empty weight of the pycnometer in water, because that's how you get your submerged fine aggregate. You determine the total weight of the pycnometer, aggregate, and water, dry another sample of the exact same mass. So Jason, what he did is he emptied out the pycnometer of 500 grams and all the water, and then was going to put it in the oven for 24 hours. That's one way to do that. The other way in lab is we would ask you to do 2 500-gram samples. So one of the 500 grams would go into the pycnometer to determine a submerged weight, and the other one we would just put it in a pan and go put it in the oven. That way you don't have to worry about trying to catch all that liquid and clean it out nice. You have the same SSD and you just dry it in an oven without having to do the pycnometer. But we get all 3 of those in lab. And then you reweigh it after the drying has occurred for your dry weight. The last test we're covering today is LA Abrasion, stands for Los Angeles Abrasion. ASTM is C131, standard test method for resistance to degradation of small size coarse aggregate by abrasion and impact of the Los Angeles machine. It's a very long title, but it's the LA abrasion test. What it does is it indicates the quality of the aggregate and its resistance to drum work. So that limestone that I showed you in the very first test, if we had some really heavy weights and tried to crush it, would it crush well? What about a different type of aggregate? Would some other aggregates break up easily when they're hit by steel balls? That's actually what the tests use. The equipment, so that on the right is what the LA abrasion machine looks like. Typically, sometimes it has a cage around it. but it just has that opening on the top with handles. You just drop all of your aggregate in there, and then you toss those charges or steel balls into the LA abrasion machine. And those steel balls that LA abrasion machine will rotate for 500 rotations, and the steel balls will impact the aggregate. And what you want, a good aggregate would be able to resist that impact and resist that work trying to break it down. So if your material breaks down pretty easily, you know your road's probably not going to do too hot because it's going to be impacted by high impact loads from cars and trucks. So you also use a sieve. You use that prior to doing the test because you want to get the correct gradation that's in the procedure next. And then you use a sieve afterwards to figure out how much of your material changed in size. You also need a balance or scale. And then, yes, those steel balls or charges. Sampling procedure, you get 500 grams of aggregate. And what you want is your blend to be 2,500 grams of material retained on the 1/2 inch sieve and 2,500 grams of material retained on the 3/8 inch sieve. So it's not the biggest. It's not like what we did with the limestone. It's a little bit smaller than that. But this allows, it helps you in your procedure because you're going to have more material in there than having a ton of large material, because you have more of it when it's smaller and it weighs the same. So procedure, you wash, oven dry it, same as always. You separate the sample according to the required grade. So you sieve it over that 1/2 inch and 3/8 inch, and then you get that material and collect it. And then what you do is you put the aggregate off 5,000 grams. You put it into the LA machine or Los Angeles machine. You toss 11 of those steel balls, and you want to turn it on for 500 revolutions. After that happens, what you do is you remove the material from the LA machine by dumping it. You rotate the machine and dump it from the bottom, and you want to sieve it over a number 12 sieve. I don't know that sieve opening size off the top of my head, and I hope none of y'all do, because we have charts for looking at that. But what you do is you want to sieve it over that. You wash the coarse material and dry it to get off any of the dust on it, and then you determine the mass of that material. You calculate the loss percentage of the original mass. So you have 500 grams of the sample, or 5,000 grams, my apologies. You have 5,000 grams, and some of that is going to get pummeled into dust, and it's going to get washed away. So you might end up with 4,990. That would probably be a pretty dang good aggregate. You might end up with a lot less than that. You also can see how that gradation changed after that machine. That's going to show you its resistance to drum work. Very good test for checking the quality of the aggregate. And just a simple little picture. On the left is a pile of limestone. On the right is right after the LA abrasion. You can see it's changed in size. It's a lot smaller. There's a lot of smaller particles in it. Still some that are big, some that are small. But that's what's going to happen. You don't want a lot of it to occur in your sample. That's what I have for this week's lab. If there's any questions, give me one moment.